motor underneath, as well as the armature arm and its shaft, and then the mainframe casting. We also put the cover on and made it an integral primary part of the structure. So we wanted to find the normal modes for this assembly now. There would be some zero frequencies possible. You might think of the rotations of both the spinning disc and the armature arm as mechanisms. In a static problem, that would doom you, but in a dynamics problem, you can have that. So in addition to those two modes, there would be the 6 rigid body modes of the total system. As I did for the components, though, I restrained those with soft springs so that rather than having 8 frequencies at 0 hertz, I had frequencies down at a couple hertz for those modes. In my physical modeling, I decided not to use any representation of the circuit boards internally or the air filter. These bodies inside would add both mass and stiffness, and they weren't available at the time, and they were changing rapidly, so I thought it was better not to get into that. So I basically optimized the system in terms of its primary structure and not so much on this secondary, and wanted to find out what the frequencies below 3,000 hertz were. Here's a figure showing the cover and a top view, and you can see the bolt holes where it's now bolted at a number of places around the periphery. Turning that into primary structure took a little bit more work than just a decorative cover. They did decide that they didn't need to see into the spinning disc, and this was going to be out of sight anyway inside a computer, so they didn't regret that decision at all. The finite element model of the assembly was actually very straightforward. I had some help from another student, Dave Seidel, who's now at NASA, and he did the rotating disc, the hub, and the spindle, and the motor. Here you can see the soft springs that I used to restrain the mechanisms involved in the armature arm and the spinning disc. You might ask whether a spinning disc wouldn't affect the modes of vibration, and there could be a coupling there. You could have the gyroscopic effects. That's an energy conserving concept and wouldn't add energy to the system, but in fact could do some kind of coupling between the modes. We neglected that in any event and decided we would assemble all of our components together. We had some solids in the armature arm and a lot of plates and beams in the other portions. The ball bearings in the bearing wells were modeled not as real structures, but rather as spiders. In other words, with some radial stiffnesses that set the shaft and the spindle off from the walls of the housing. These stiffnesses were given to us by a Japanese ball bearing company that was going to provide the bearings for this system. And they were really good about giving technical data, and they had measured values for the stiffnesses of their ball bearings. Typically, the shaft would be, in this case, vertical, with the mainframe casting having a kind of a well here. It actually looked like a hollow tree stump. And then your ball bearings would be located in a race at one end of the shaft or the spindle as well as the other end. So the shaft then was confined between these two ball bearings and then had something happening out at this other end, either the armature arm or the spinning disc. All told, our model had 3,064 degrees of freedom with some 500 elements and 900 grids. Here's the mesh for the system. Because I'm using this stick model, or sometimes called wireframe model, without any hidden line removal, you can get the always obnoxious optical illusion, which will make this picture alternately flip with the walls going away from you or toward you. I seem to have an easier view with this wall projecting toward me right now, so I'll view it as that way. Here's the armature arm then, which would be actually on the far side under that viewpoint, with the well here for the shaft. The motor and the spindle would be here with a spindle protruding through the floor of the casting, the mainframe casting. The rotating disc is shown here, a rather simple model with only some 8 segments around the periphery. The cover is shown on the what would, in my view of this image, is at the bottom of the disk drive. So I'm looking at this from the underside, basically, where the 2 walls to me are pointing up out of the page toward me. So this is a system, and we're interested in how this behaves. We're interested in the natural frequencies and mode shapes. The main idea is how flexible is this arm, and how well can it track the concentric circles that are written on this disc. I tried to visualize what was going on here and thought that maybe tracing out a flexibility path would be a good way to think of this. In this figure, I'm tracking that a source of error then would be the relative displacement between the tip of this arm and the relevant track here on the disc. Well, that involves a flexibility really down the Winchester head, through the outer part of this armature arm, through the base of the armature arm, into the shaft over here, into the flexibility of the ball bearing, into the bearing well, into the floor of the mainframe casting, into the other bearing well, through the bearings, through the spindle, through the hub, and ultimately out on the disc. So that if this is vibrating either in a slewing direction or vertically, then it's going to cause problems in tracking here. Interestingly, at the time we were doing this, we were trying to track on information that was spaced 1/1000th of an inch apart, but at that time there was a Japanese laboratory that was doing compact discs, as I believe, in retrospect, and they were putting down tracks that were 12 millionths of an inch apart, and with I think that was like a 10 millionth of an inch track with a 2 millionth of an inch gap between the tracks. In any event, I know in metric it's hard for people to figure that out easily, but there's a fact they were doing in a laboratory setting with air-bearing spindles. They were tracking 80 times more accurately as we were, and to do that they had to have not only electrical control at the root of this arm, but they also had another spot here like a wrist with another pivot, and they could do vernier corrections on the gross motion of the body. And that was a laboratory situation where I imagine this was a $100,000 device that I'm describing now, whereas the one that we were trying to develop here was to have been $500 or less. So certainly how much you can accomplish has to do a bit with the budget that you have. Now, I remembered also that during summer trips with my family that we often got into a situation with 3 little kids in the back seat that they would get thirsty and want to drink, and then my wife might be sitting in the passenger seat in the front and would grab say a half gallon of water and lean over the front seat and try to pour water into a cup being held by a child in the back seat. And you can about imagine how that goes. It would be very similar to this, that the flexibility of the entire automobile through my wife's arms and down into the seat, bouncing around in the body of the car and into the back seat, and with the kid finally holding the cup, and you got all this jiggling and joggling. You can see that there is a total flexibility path there that makes it hard to position something precisely. I'll show 3 figures for the mode shapes on this total system and then give a table with some more frequencies as well. The first mode of this system is characterized by bending of the spindle here on which the disc is spinning, and you have the relatively heavy magnetic material that forms the motor. The bearing well, you can see, is tilting as well. Now, this is, of course, again, an exaggerated motion, and nevertheless, though, you're seeing where the dominant flexibility is. The spindle was about a 1/4 inch steel rod, and so that wasn't exactly a weak namby-pamby structure, but yet relative to the weight that it's being asked to carry here, and I should discuss it in terms of mass, this mode is the lowest mode. Now look how the disc is going up and down on this. And again, when I showed pictures of this to my electrical engineering acquaintances, they were worried about this. My gosh, the disc is going outside of the chamber that it's supposed to be spinning in. And look, the read-write arm is going the other way. Well, those are important relative positions, but the amplitudes are not important because that's not scaled, as we've discussed a number of times. But this would require some flexibility then in the Winchester head then, because as with the vinyl disc on an older phonograph, you would need some vertical play here to keep tracking the same circle of data. But we are happy that this is above 500 hertz, and so our lowest frequency in the system was acceptable. The second elastic mode is similar to the first in the sense that it's primarily a bending of the spindle, but it takes place in a plane that's orthogonal to the first elastic mode. In this view, it doesn't show up so well. You can see what's happening, though, because the disc is tipping in a different plane, and we see the flat of it here. Again, though, the read-write arm is moving upward here, and at that point, the disc is not moving as much. So this is definitely a motion in a perpendicular direction from the first bending of the shaft. See how the motor itself is being tilted here, the magnet that makes up the motor. The third elastic frequency of the system is largely an armature arm flapping, shown here. And again, I had to calm down my electrical engineering friends and tell them, no, it's not really flapping outside of the disc chamber. We're getting a little bit of motion of the cover of the chamber as well, which was interesting. About the only time that we got anything going on with the cover. So it's interesting to look at the mode shapes and see how it might affect the tracking of the system. Again, the frequency above 500 hertz, so we're in pretty good shape now, and I'll tabulate these in the next figure. Here I'll show the tabulation of frequencies with some names about mode shapes. We show 2 different studies for the assembly. One was the assembly without the cover, and the other is assembly with the cover. We also can hearken back to the mainframe solution standing alone. When you add the gear onto the main frame, consisting of the armature arm and the spindle with the motor and disc on it, you actually lower the system frequency. And that was what we had expected initially, that the assembly would have lower frequencies than the components individually. But when you put the cover on, then you stiffen it up quite a bit. So that cover really was helpful and brought us into the safe region. Likewise with this higher mode here, as we put on the armature arm and the spindle with its motor and discs, we got this frequency at 303. These are relatively close because the real source of flexibility here is in the spindle, not in what the sidewall is doing. Finally, if you put on the cover, it raises that second frequency nicely as well. The third frequency, which we thought of as an arm flap here, was up a bit higher initially and then was raised nicely by the stiffening of the cover. There really is an open question about the mode tracking. I can really not guarantee you that this twisting mode really is an integral part of this particular action and not this. You'd have to make minor parameter changes, and this was an enormous change in the system. So the logic is a little bit weak on my mode tracking from this number to this one and this one to this one. I think there would be a lot of blending of the mode content of these two into both of these behaviors, but that could be unscrambled if you could do some sort of a gradual assembly, put on one little component at a time. Interestingly though, we did pick up the disc bending modes. They occur down here at 748 Hertz and 750. The only difference being the slight amount of non-symmetry between the fore and aft and the side-to-side vibration. That would be because the sidewalls would add a little more stiffening compared with the open ends of the system. Unfortunately, the attempt to come out with the first mass-produced disk drive for PCs failed. Irwin International went bankrupt, and the surviving effort in that entire project turned out to be the relatively fast tape recorder that was put in it, and the tape drive could record the entire amount of information on that disk in just a short time. I think the number at the time was 2 minutes for the 5 megabytes. Now those rates are not high in today's market, so this was certainly an early attempt, but a very good attempt. It also reminds us though that even though you work hard on the engineering side, you also have to do a good job on the manufacturing side. And I heard critics of this project predict the failure because of manufacturing right from the outset. From the day I walked in to help these fellows as little as I could, there were other computer people in town that were saying that they'd never be able to make it. And that did turn out apparently. But what a noble try, and had they succeeded, they would have been an enormous company by now. You've seen other disk drive companies that made it and are just enormous companies now. So what a good try at making one of the first compact disk drives. If I understand right, the problem in production was that they were getting flaking off of the aluminum castings that would get onto the disk, and that they tried new materials in the read-write heads, in the Winchester heads, that also contaminated the disk. The particular model that I have in front of me, when it was initialized, apparently scraped off, because of so many crashes, scraped off the magnetic media over the bulk of the surface. And so the model I have here was one of the ones that was unfortunately not able to make it into production and couldn't even make it through test. Well, I did use this particular study, though, as a motivation for some of my own doctoral students. Kyuk Kim and Curtis Hoff were two doctoral students who used the mainframe casting as a model for trying to work out what we call nonlinear optimization through perturbation methods. I challenged each of them to raise the natural frequencies of the mainframe casting to 500 hertz or higher, the same challenge that we had had earlier. This time, though, not by adding a cover or adding small stiffeners, but rather by changing the thickness of the casting in the different regions. In the next figure, you're going to see the results where it shows changes that are substantial, above 30% changes. That was a good workout for our nonlinear perturbation methods, where we carried higher order terms that are neglected even today in optimization, even though it's becoming a fashionable thing to do with linear sensitivities. We actually were ahead some time ago on how to do this, but never commercialized the process. People involved were myself, Sandstrom, Bernitsis, a faculty member in Naval Architecture, Kim, and Hoff. National Science Foundation put some money into this at the outset, didn't want to put money in later to commercialize it, and probably that's consistent with their general goals. We came out with 3 AIAA journal papers and were able to show these results in a kind of a nice, concise way. This final figure shows some of the thickness changes that were prescribed by the method that Kurt Hoff used. We asked for a plus 34% change here in the floor at that point, 48% increase on the floor here around the armature arm bearing well. There was a 25% change in the thickness of a stiffener here. But there were some reductions in thickness on the side walls. Kurt and Kyuk both did a kind of study here where they not only maximized the stiffness of this body, but they also minimized the weight. And so they were able to gain that added frequency and actually reduce the weight a bit. So it's an example then of the kind of optimization that's being done now more and more, where you have constraints such as our frequency constraint to be higher than 500 hertz, and then you have an objective which is perhaps in this case to minimize weight. So that's the end of our case study.